So we'll continue the discussion of the Green's function. Right, so let me just write it. So you remember that we had, so I mean, I think let's concretely look at the second order differential operator, right? So this was some a d2x plus b by dx plus c. So this is going to act on some u, and essentially we are looking at equations of the type Lxu equal to 0 for the homogeneous, or some, if it is non-zero, it will be a inhomogeneous differential equation, right? Then we said that, okay, and L dagger x was if I remember correctly, I mean, yesterday we had obtained this expression. I think it was d2 by dx2 a bar plus, do you remember that expression? There was a factor of 2, I think, right? 2 d a bar by dx, d a bar w, right? 1 over w minus b bar. Right? So 2 over w, this thing. That thing was d by dx. And finally, there was that was a much more complicated term, plus c bar plus d2 w a bar 1 over w dx2, and then there was a minus 1 over w dx. Right? This was the operator, and now the boundary term. And the boundary term, again, I now q uv bar was, unfortunately, do you have any of you have that? Sorry, I mean, otherwise you'll have to again work it out. Do you have it? Let's see. So it was, it was w b bar u. All of this evaluated at between x1 and x0. So I will just write it like this: x1 and x0. And then there was minus b by dx acting on w v bar a times u. All of this evaluated between x1 and x0. This was the expression. Thank you. Okay. Now let us just to get some idea about. I mean, under what condition this L dagger could be equal to L? Okay. Sorry, just one thing. Yeah, you remember this discussion here was that there is given some boundary conditions on U. These two boundary conditions. We need two boundary conditions on U. You can always find the corresponding boundary conditions on V in such a way that these boundary terms vanish. Right? One more thing I will do. I mean, from now on, we will always use homogeneous boundary conditions. Okay. So in other words, for U and V, the boundary conditions will look like some alpha U x1 plus beta du by dx at x1 plus gamma u x2 x naught plus delta du by dx at x naught. This, I mean, in principle, you could put as some inhomogeneous term here, right? But we will put always homogeneous. So right hand side will be 0. Okay, and so boundary conditions are this: some alpha prime u x1 so it will be, we'll choose it to be homogeneous. The reason why one is choosing it homogeneous is because if it was inhomogeneous, you see then the corresponding set of functions which satisfy the boundary condition will not form a vector space, right? I mean, see, if you have two functions which satisfy these boundary conditions, if you, okay, then if you add those two functions, suppose u and u prime satisfy this boundary condition, right? Then u plus u prime also will satisfy the same boundary conditions. But that is because the right-hand side is 0. If the right-hand side was not 0, then u plus u prime will not satisfy the same boundary condition. It will satisfy with twice those values, right? So that's why. So if you choose it to be homogeneous, then so what it means is that because it's homogeneous boundary conditions, BC will mean boundary conditions, implies that the set of functions that satisfy the BC, that satisfy these boundary conditions, forms a vector space. So I will always be using now the homogeneous boundary condition throughout now. Maybe next week we will see how to deal with the inhomogeneous boundary conditions. But for the time being, we'll just work with the homogeneous. Sorry? There are two conditions, yeah. Alpha and alpha prime. I mean, those coefficients are different. No, boundary condition specified by giving these parameters, alpha, beta, gamma, delta. Yeah. I mean, I remember I gave you an example. Suppose, as an example, suppose I choose alpha equal to gamma equal to delta equal to 0, and alpha prime equal to beta prime equal to gamma prime equal to 0, then this boundary condition is just Neumann, right? So this tells you, I mean, and of course, when 3 of them are 0, the fourth guy is not 0. Otherwise, this will be identically 0, right? But we want this to be linearly independent, these two. So this implies that the boundary conditions are simply du by dx at x1 equal to 0, and du by dx at x0 equal to 0. So that's a Neumann boundary condition. Okay. You can choose differently. For example, you can choose, say, beta, gamma, delta equal to 0. That means u of x1 is 0, right? And similarly, you choose alpha prime, beta prime, delta prime equal to 0, then u of x0 is 0, right? So by choosing different possible alpha, beta, gamma, delta, and alpha prime, beta prime, gamma prime, delta prime, you are just changing the boundary conditions. They have to be linearly independent. Important point is they are linearly independent. Okay. So if all of this, if ratio of alpha prime and alpha is equal to ratio of these two guys equal to that, then they will be linearly dependent, right? So we don't want that. We want linearly independent. Because if that was the case, then there will be only one boundary condition, and that's not enough for a second order differential equation. For a first order differential equation, only one boundary condition is needed. I mean, that already specifies. In general, if you have nth order differential equation, you will need n boundary conditions to specify the solution. Okay. Yeah, so this will be homogeneous. And I again, just to recall, this is an important point to realize that you see that, I mean, this statement that you can always find a boundary condition on V such that this surface term vanishes, right? That is because, and in fact, and moreover, the boundary condition on V will be of the similar form with, of course, different coefficients in general, right? So the reason is that if you look at this expression here, sorry, there is also one more term, right? There should be a du by dx also, isn't there? There should be one more term. Yeah. I mean, there is also one term which involves a derivative of u, right? Which is where is it an extra piece apart from this? you have, can you read what is that?
d by dx.
So there is another piece. So plus
Plus d by dx. Omega.
uh-huh,
V.
v bar
V bar, yes.
uh-huh, a and then du
Yeah. No.
du by dx.
No.
The whole thing. Okay. D by dx. Is that?
Yes.
Are you sure? I mean, yeah. I mean, certainly there is one term which involves a derivative acting on u, and then there are terms which involve no derivatives on u, right? So, but I mean, now using these boundary conditions, using these two linearly independent equations, you can see there are four quantities here: this, and that, right? I mean, the u at x1, u at x0, and the derivatives at x1 and x0. So using these two equations, you can eliminate two of them in favor of the other two, meaning you can express two of them in terms of the remaining two, right? Okay. Now you go back and plug that. So everything will not depend on just those two independent quantities. Sorry? No. That was an example. I'm saying that just take now general. Take a general. That was just an example to show that it is possible. So I mean, again, so what I'm saying, so let's suppose that I, for example, using this equation, two equations, I can eliminate du by dx and du by at x1 and du by dx at x0, and I can express that as a function of in terms of u at x1 and u at x0. After all, there are two equations, right? Four unknowns, so you can determine two in terms of other two. Okay. So suppose that these two guys I can determine in terms of this guy and that guy. Okay. Then I plug that back here. Wherever I see du by dx appearing there, because these are always the endpoints, right? x1 and x0. I can replace them by u at x1 and u at x0, right? So now if you look at this whole thing, there will be two terms, u of x1 and u of x0, right? Now the coefficient of u of x1 will be what? Will be again the v bars, the v bar and the derivative of v bar at point x1, right? Similarly, u of x0, I mean, right? You understand? So each of them, the u of x1 and u of x0, the coefficient of that will be a linear function of the v bar at the endpoints and the dv bar over dx at the endpoints, right? So now just equate the two coefficients equal to 0. Okay? So that will give you two conditions on the v bar, right? Now on those conditions will be exactly the similar type. There will be linear functions of the four quantities, v bar at x1, v bar at x0, dv bar by dx at x1 and dv bar by dx at x0. So there will be similar equations, right? Okay. Is that clear or not? Because we want the surface term to vanish. We want the q to vanish, right? I mean, if you want q to vanish, then I'm saying that you can accomplish that by imposing some particular boundary conditions on the v. And those boundary conditions will be similar in form, except these coefficients will be different. Alpha, beta, gamma, delta will not be the same. It will be different. But it will be similar in form. I mean, you need to do that, otherwise this equation is not true, right? I mean, after all, you want to call this as adjoint of that, right? If that is the case, then this should be true, that dx, wx, say u, L dagger, u bar, L dagger v, or let me take the complex conjugate, v bar, okay? That should be equal to dx, wx, v bar. No, probably I think it's not this. Sorry, v, no, okay, lxu. When I do that, so this is supposed to be equal to, I mean, this is the same as what we are saying, vlu, and that should be equal to, by definition, u, L dagger, v complex conjugate, right? That's what, so it's a L dagger v, so this is u bar, so I take this here, this is complex conjugate of that, right? This is what we should have, but what we saw was that this minus that this minus that was equal to this boundary term, Q U V bar. Right? Remember how you obtained that. We just started doing the integration by parts. This is the Lx is that. Start doing integration by parts. So then you will get the L dagger. Right? But in that process, you had this boundary terms. Those are the boundary terms. Right? So if you, I mean, for this equation to be true, you better make sure that the boundary term vanishes. Right? That is the idea. So and that it was not guaranteed, right? I mean, it was not obvious that you can choose some conditions on the V, some boundary conditions in V, such that this is always possible to make it vanish. But what I'm trying to say is that it is possible actually. In fact, not only it is possible, it just gives you again two conditions on the V, which are of similar type, similar form. Linear equations on the V at x1, V at x0, dV by dx at x1 and dV by dx at x0. So the similar form. And those boundary conditions are called adjoint boundary conditions. So you see, so what is happening is that the L is going to act on the space of functions defined by this boundary conditions, whereas L dagger will act on space of functions which are defined by the boundary conditions on the V, which is obtained by demanding that this vanishes. I mean, let's take some examples. I mean, this is true, right? You agree? All of you agree that this formula is correct? I mean, huh? This is du by dx. Yeah, I think that is what we thought. Yeah, it should be du by dx.
And it is B W V bar. There is
B the there's another term besides that. Let's see.
here, and then here.
So how many terms? This, and this? Huh?
Yeah. Yeah, 3.
That's all. Okay. So let me just see. So we have W V bar B, that is this term. Yeah, this term. Then you have U times that with a minus sign. Yeah. That should be A, right? And then finally, W V bar A. I mean, let me see. This is, but there is no term involving U derivative on U. And there should be a derivative in U. Okay, let's just do it again. So here, let's see. So I start from this expression, right? So this expression. I do a partial integration. So first term I will get is, so start from here, no? So you get here W V bar A du by dx, right? That's one boundary condition. Because when I do 1 d by dx outside, I will get that, the boundary term. Then I will get, so there's a minus sign. So now the derivative has hit already this guy. So dw v bar A by dx, and then u. Okay, again with the endpoints. And this one is easier. So that's plus w v bar B u. Yeah, that's what it is, right? Yeah, in fact, that's what it is. Yeah. This is exactly the expression. Right, that's fine. Okay, so let's now try to just to take some examples. Just to take an example to see, because maybe this looks a bit abstract, this counting of numbers. So let's just take a simple thing. I mean, suppose to simplify, let's suppose W was 1. Okay. So take some example. Say W is equal to 1. Okay. This is a simple case. And let's take, say, for the initial thing, I just choose Neumann boundary conditions. Let's suppose du by dx at x1 equal to 0 and du by dx at x0 equal to 0. Say this is a Neumann boundary condition. Now then we want to ask what boundary condition I should choose on V such that this surface term vanishes. So let's see what are these. So du by dx, anyway, this term disappears because du by dx at the endpoints are 0. So this is not there. So only things you have is here. And what you find is that, say W, actually I didn't even, okay, say W is 1. Let's keep W as it is. So then the condition is W B V bar. So what we have is this whole thing evaluated at x1. I mean, when I write like this, see, these are all functions of x. So what we are saying is this at x1 times this at x1 times this at x1. Okay, that is a term coming here at x1, and then minus d by dx acting on w v bar a. Evaluated it again at x1. This is multiplying u at x1, right? And then there is a similar expression which is the same thing, just evaluated at x naught. Evaluated at x naught. This is multiplying u of x naught, right? And we want this to vanish. But u at x1 and u at x0 are completely arbitrary, because only boundary condition for u is this, right? These are completely arbitrary. Okay, so the only way this can vanish is that independently this is 0 and that is 0, right? So that gives you a condition on the v bar, because these are all known given functions. These are functions which are given to you. W, b, etc. are given to you, right? So you can just open this up and so there will be a term which involves without any derivative, there will be on the v, and there will be a term which involves a single derivative on v, right? So again, the expressions will be of similar form, you see. Actually, in this case, what we call, this is an unmixed boundary condition, you see. Unmixed boundary condition is in the sense that one boundary condition only depends on the value of the v at x1 and its derivative at x1. It doesn't care about the corresponding values at x0, right? And this equation, when you set this equal to 0, you see everything depends on x0, right? So the two boundary conditions are separate. The boundary condition at x1 and the boundary condition at x0 are separate. They don't mix. The reason why that happened is because the original boundary conditions I chose for u were unmixed boundary condition, right? It was something at x1 was 0 and something at x0 was 0 separately. That's why finally you get also unmixed boundary conditions. In fact, furthermore, let's suppose for simplicity, suppose the w and so let's say w is 1 and say a is 1. Okay. In that case, this derivative w and a are constant, so you can take it out. So it's simply d by dx v bar. Right? So furthermore, so let's assume further just to see how it is. So let's take w equal to a 1, a equal to 1, and further also simplify b equal to 0. So in other words, we have this differential operator is simply 1 times d2 by dx2. This is not there, plus some constant. Okay, that's the original differential operator. Okay, and with a w equal to 1, in this case you see this term drops out because b is 0. Okay, and the condition that you get is that the d by dx of v bar at x1 should be 0 and d by dx of v bar at x0 equal to 0. So again the Neumann boundary conditions, right? So what we are seeing is that if a equal to constant, I mean need not be 1, a equal to constant, and this is not there, and okay, and c could be anything, c need not be a constant, then this differential and if you had chosen the Neumann boundary condition for the origin for the u's, then for the v also you get a Neumann boundary condition. Okay. Huh? No, because you see that this is happening only because I chose these things. In general, no. Yeah. Actually, furthermore, you can see that under this condition, you see what is the adjoint operator? Let's see, this is not there, right? Because we are under assumption b is 0. This is 0 because a and w are constant, so the derivative is 0. So again, the first derivative does not exist in the Dagger. Here again, you see this is not there, b is 0 anyway, and this also everything is constant, so this is also not there. So you just get back again c bar. So L Dagger is simply a bar d2 by dx2 plus c bar. So if a and c happen to be real, if you had chosen them to be real, then L dagger would be equal to L. Huh? You see. So in that case, this operator would be the self-adjoint. L dagger is equal to L. Only in that case, I mean, under these conditions. So I'm saying that under these conditions, and furthermore assume that A and C are real. Okay. So if you assume this, then L dagger is equal to L. And furthermore, if you had chosen, say, for example, Neumann boundary condition for the original space, right, the space in which a U lives, then the space in which V lives is also the same Neumann boundary condition. So this is an example of a Hermitian operator. You see, if it happened that you had L dagger was equal to L, but the boundary conditions were different in the U space and the V space, then you don't call it Hermitian operator. You just say a self-adjoint operator, that's it, but not Hermitian operator. You say something is Hermitian only if the space on which it acts is also the same. Okay? So the boundary conditions also should be the same. In fact, it's not just, I mean, under these conditions, it's not, I mean, you could have also chosen Dirichlet boundary condition. For example, suppose U, the Dirichlet boundary condition is the U of x1 is 0 and U of x0, x0 is 0, right? That's the Dirichlet boundary condition. Value of the function is vanishing at the endpoints. This is what's called Dirichlet boundary condition. If you had done that, you see now you go back here, then these will vanish, right? Because this involves the U at x1 and U at x0. And also from, but this will not vanish in general, right? I mean, this du by dx at x1, which is multiplying v bar at x1, right? So, and du by dx at x0 multiplying v bar at x0. And they have to be independently vanishing, right? So that tells me that v bar at x1 should be equal to 0 and v bar at x0, x0 equal to 0, you see? So again, Dirichlet boundary condition remains invariant, remains the same. ABC, well, I mean, actually, for the Dirichlet, I didn't even need, for the Dirichlet condition, this disappeared anyway. So the only term was that, right? If I had chosen Dirichlet boundary condition for U, these two terms vanish anyway, right? I mean, what is the Dirichlet boundary condition? Dirichlet boundary condition, a condition is U at x1 equal to 0 and U at x0 equal to 0. These are the Dirichlet boundary conditions. So under these conditions, these two terms can disappear because this object evaluated at x1 and x0, right? Similarly, this object evaluated, but there is a U there, so that's 0, right? So then only term which is left over is that, right? So du by dx at x1 and du by dx at x0, right? With some coefficient. But since du by dx at x1 and du by dx at x0 are independent, right? Therefore, coefficient must vanish. And for the coefficient to vanish, you must have v at x1 and v at x is not equal to 0, right?
That is where I'm asking a question. If A is a function.
But non-vanishing. Suppose A is not vanishing at x1 and x0, right? So if A is vanishing, so let me ignore all these situations. It's a singular situations where A might vanish at some points and so on. No, let me ignore that for the moment. So suppose A is not vanishing anywhere. Okay. Because A is vanishing is a bit strange because if A vanishes, then you see it becomes a first order differential operator essentially, right? At some points it may happen. So let me just ignore all these subtleties. We will come back to this more complicated situations when we discuss hypergeometric equations. For the moment, I'll just assume that A is not vanishing. Okay. W of course is not vanishing. W is a weight function. It's positive one. So what this tells you that V at x1 and V at x0 equal to 0. So Dirichlet boundary conditions are also self-adjoint in some sense. I mean, yeah. Actually, that is happening even when without any of these choices. For Neumann, we had to choose some particular behavior. Okay. So now, what I wanted to say is. Yeah, I mean, so in fact, now let's try to see under what conditions. So for the moment, let me ignore boundary condition. Let's just look at this two. Under what conditions this could be, I mean, self-adjoint. And now let me assume that W is 1. Okay. So let's consider W equal to 1 case. So I will assume the weight function is 1. So now then L dagger simply becomes, L dagger x simply becomes A bar d2 by dx2. And then here you get W is 1, so this goes out. So you simply get 2 dA bar by dx minus B bar d by dx. And then here you get plus C bar plus d2 A bar over dx2 minus dB bar over dx. Right? This is the operator. And we want this to be the same as that. So we are asking, how can I make L dagger equal to L? In this case, in this simple case, so W is 1. Well, from looking at the second order differential operator, this already sees that A bar should be equal to A. So A must be real function. I mean, it need not be constant, real function. So this is all, I mean, these are all functions of x. Many times I don't show explicitly, but what it says is a real function. A is a real function of x. But now look at this one. We want this to be equal to B. Okay. So what it is saying is that therefore B plus B bar, I mean this is equal to B, so I just take it on the other side. So B plus B bar is equal to 2 d A bar, but A is real already, so I can as well just write this dA by dx. Right? So what we are saying is the real part of B, again B is a function, right? So the real part of this function is equal to dA by dx. This is consistent, of course, because this is real, but that's also real, because we have said A is equal to real, right? And finally, if you look at this equation, so what this is saying is this should be equal to C. So what we are saying is that C minus C bar should be equal to, C minus C bar equal to d2, well, A is real, so d2A by dx2, dx square, minus dB bar by dx. So let me write it like this, minus d by dx, B plus B bar, 1/2, let's say, and then minus 1/2 or plus 1/2 d by dx, B minus B bar. Okay, so all I did was just added this B and subtracted the B. I mean, this is what it is. C minus C bar is supposed to be equal to that. Okay, this I wrote as it is because A is real, so I can just forget about the A bar. A bar is the same as A. Okay, here what I did, I just added and subtracted B. Okay, I mean, this was originally minus dB bar by dx. Indeed, you can see the coefficient minus half dB bar by dx, and this is also minus half dB bar by dx. So that makes it minus dB bar by dx. And the dB by dx cancels because this is minus half and that's plus half. That cancels. So that is original. But now in this form, you see that this is equal to that anyway from this equation. Right? So this cancels that. And what you are left with is simply that the imaginary part of C is equal to the derivative of the imaginary part of B. Half the derivative of the imaginary part of B. Right? Again, it's consistent. I mean, so this is the only condition for this to. In particular, suppose B was also real. I mean, suppose I had chosen B also real, then this equation is, and then this equation basically says C must be also real, right? Because if B is real, then this vanishes, then C must be real. Okay? So the one possible choice is A, B, C real, but so in the real case, 2B is equal to 2 dA by dx, so therefore B is equal to dA by dx. So let me consider that case. I don't want to erase this part. So let's consider this. So we are saying A, B, C, all real. Okay, it need not be. You see, it could be as I said, B and C need not be real. But then the relation imaginary part of B is related to imaginary part of C with this equation. But let me ignore that. Let's assume first of all of them are real. A, B, C are real. So you have this. And what it is saying is that the condition is, in this case, 2b is equal to 2 dA by dx, so therefore b is dA by dx. So then this Lx operator is simply a d2 by dx2 plus plus dA by dx d by dx. So let's say Lx acting on u is the same as that, yeah, plus Cu. Okay. And this we are saying is adjoint. But in fact, you can see why is that so? Because these two things together, I can write it as d by dx acting on a d by du by dx. Right? These two things. And that's the reason why it's self-adjoint plus Cu. Because you see now, if you look at this expression, if you start from this expression, remember how we got L dagger by doing partial integration, right? So you multiply this by V bar and take the dx. Remember, in this entire discussion, I have taken W equal to 1, right? So there is just this 1, W is 1. Now when you do partial integration, forget the boundary terms, then what you will get is, again, you see first d by dx will act here, right? Then you have the A, and then again d by dx. So it will be exactly of the same form as before, you see. And for C, there's nothing, it doesn't matter anything, because C is it's no derivative, so it's as it is. That's why L dagger is equal to this form. More generally, if you had a W, if you had some non-trivial W, still, if you had chosen Lx to be of the form, Lx to be of the form 1 over W d by dx with some function p, okay, again, it's all function of x, I'm not writing x, but some function of p, d by dx, okay, so let me write it, Lx acting on u is this. So this d by dx acting on the combined thing, plus c x u. Then this will be again self-adjoint with respect to the weight w. Okay. For the same reason, now let me erase this here. For the same reason, because then again, if I take v bar times now there's a weight function w dx, and here I have the Lxu, but Lxu is 1 over w d by dx p of x du by dx. Okay, I mean this is acting on everything, plus c x ux. This is what it is. But now you see that, so let me multiply the w inside. Okay, so when you multiply w inside, this goes out, this w goes out, and there you get a w. Now you do two partial integrations, then what you will get is again the same form, you see. So what you will get by doing, so first partial integration gives me d by dx acting on v bar, right, with a minus sign. I'm not worrying about the boundary terms, just looking at what you get here. Then I'm left with the p here, and then I do a second partial integration. With the second d by dx, I move it across. So I will get d by dx again here, right? There will be two minus signs, so combined thing is plus, because each time I move it back, there's a minus sign. So it becomes plus. And then again, and times u. Okay. So let me multiply and divide by w. Then you see this is what you have, right? And there you have just cv bar. So this is what we call L dagger. So L dagger is simply of the same form as that, of the same thing as that. L dagger is equal to L. Again, I'm assuming here P, C, etc. are real. Otherwise, there will be complex conjugation required. I'm assuming P and C are real.
The last term, which is like a momentum operator, d by dx.
Actually, yeah, this part that I ignored the imaginary part. That imaginary part is the momentum operator. Yeah. Yeah, correct. In fact, I mean, suppose that B was constant imaginary, constant, independent of x. In that case, of course, this will be 0. So the imaginary part of C will be also 0 again. And then the imaginary part of the operator is simply the momentum operator, which is, you remember, momentum operator is d by dx times the I, or 1 over I, which is the same, essentially. So that's what it's giving you. That if you want a Hermitian operator, which is just d by dx itself is not Hermitian, right? You have to multiply by I to make it Hermitian. So that's what's happening. Yeah, so what we are saying is that, I mean, although this analysis I did was for w equal to 1, this previous analysis, but in general, for any w, this, if the operator is of this form, okay, if the operator is of this form, then L dagger will be equal to L, provided P and C are real. So that immediately tells me one important thing. So let's just open this up and compare with this. Let's open this up. So what we are, okay, first of all, let me just write this again. So for such an operator, L dagger is equal to L as a formal operator. I'm not saying that the boundary conditions are the same. I mean, we have not analyzed the boundary conditions, but just as a formal differential operator, they are the same. So let's see. Let's just open this up and try to compare it with this here. When you open this up, you get that Lx is equal to P over W times d2 by dx2 u, right? Then there will be a first derivative term, which will be 1 over W dp by dx, du by dx, plus cu. Okay. Now compare these two. So then you see, for this to be Hermitian, again assuming A, B, C are real for that case, then we have the following condition, that A must be equal to P over W, and B should be equal to 1 over W dp by dx. Okay. So in other words, if A and B satisfy these equations for some P, for some real P, right, then this would be self-adjoint with weight W. So now let's see, from this equation, I can of course eliminate W by taking the ratio of the two. So this implies, so let's take this equation divided by that equation, right? So then you'll get dp by dx, and then when I divide by P over W, you get 1 over P, W cancels, okay? That's equal to B over A. Therefore, the solution of this equation is P is equal to P is equal to exponential, yeah, e to the power of the integral B over A. P of x is up to x. I mean, this is indefinite integral, right? Exponential. This kind of things appeared before. Remember when we tried to solve the second order differential equation? I mean, this things when we said that if one fundamental solution is given, how you will get the second fundamental. So in doing that, we encountered these exponentials, right? Okay. So of course, this can be always done. I mean, for any B and A, I can find a P given by that equation, right? But what is not, but that doesn't imply that this A is equal to P over W. You see, there's also an equation which, I mean, here we just took the ratio. I mean, that's only one combination of these two equations. There's another independent equation, which is the value of W, right? So what it says is that W, therefore, from here you see that W is P over A, right? This means it should be of this form, e to the x naught to x, B over A, dy, and 1 over A, x. If the Wx is that, okay, then this this differential, this operator will become self-adjoint. But this also establishes one important fact, that no matter what A, B you have chosen, real, I'm assuming it to be real, A, B, C are real, okay? No, I can just construct a W, a weight function, for which that operator becomes self-adjoint, right? You see? That is important because you see, when I'm asking for a solution of an equation, say Lx acting on U equal to some function, right? I don't care about, I mean, that differential equation makes sense without talking about any weight function, how you define the inner product. You don't need all that. I mean, I have just a differential operator acting on some function equal to something, and I want to find that function, right? So W is not, I mean, W has never entered in that equation, right? So in principle, you can solve that equation without knowing anything about W. But what we are saying is that I can construct a W, given an operator, I can construct a W such that that becomes a self-adjoint operator, okay? Which will be important for the Green's function techniques. I mean, Green's function analysis becomes easier if you are working with the self-adjoint operators. Although you can do it for general. In fact, the way I will present it will be for general operators, not necessarily self-adjoint, but it becomes easier for the self-adjoint operators. So you can always find a W for which this is self-adjoint. And in fact, maybe for this kind of an operator, I can also simplify this expression. I mean, this Q. Actually, maybe we can make it simpler. So W times A is simply P, right? W times A is P. So let's see what is Q. Q for this kind of operators, U V bar. This is WA is P, P V bar du by dx at x1, x0. And then, sorry, this need not be x0. And this is because I'm using x0 for the boundary. This is any point. I mean, I don't know, any point. What shall I call x2, let's say, some point. You can also choose x0. It doesn't, I mean, this is up to you. But the important point is this should be independent of x. So that, and then what about W times B? W times B is dp by dx. So plus dp by dx v bar u at x1 and x0. And then you have minus, again, WA, which is P. So d by dx, PA, PV bar, sorry, PV bar, U, acting on x0. In fact, it becomes very symmetric because now you see these two things I could combine together to write this as simply, you see, these two terms together is simply P, U, P, if you want to write it like that. If you want to write it like that, it becomes like that. So it's very completely symmetric in somehow. So, I mean, now you can check various things. I mean, so for example, let's see if initial boundary conditions are, let's say, Dirichlet. So U at x1 equal to U at x0 equal to 0. So say these are the initial boundary conditions. Then what it says is from here, you see this term anyway vanishes, and from that term you simply get, I mean, the term which will be relevant is of course du by dx, but that will come with the PV bar. Okay. P is not 0 anywhere. P is this, the exponential. Exponential is not 0. So what it tells you that this implies that V at x1 equal to V at x0 equal to 0. Okay. Because this has to vanish. For each du by dx at x1 and du by dx at x0, the coefficient of that must vanish. So you get that. Yeah.
Apart from the fact that A is a real function, is there another condition?
No, A has to be positive. I mean, if I want to write this, A has to be positive. Yeah. Because if I want to use it as a weight function, then A must be positive. Correct. So A is real. So this is, yeah. I mean, A is real and positive. Okay, that is because we want to use it as a weight function. Weight function has to be positive, right? This is anyway positive, exponential, so A must be positive. Okay, the second, if I take the Neumann boundary condition at x1 equal to du by dx at x0 equal to 0. Let's see what happens here. So in this case, du by dx cancels. And if you now look at, so if you combine now, so what is happening? So we have to open it up. I mean, it's better to open this up. Actually, you see, I could have simplified this. Sorry, I could have simplified this at both systems. These are the expression, right? This is the whole thing. So the term which comes to the dp by dx, I mean, this derivative acts here also, right? dp by dx cancels between the two. So I could have just simplified it, in fact. Okay. So this p comes out actually. So the only term which survives here is that. Okay. So since p is not 0 anywhere, so actually this is what we want to vanish. What we want. Sorry, this is becoming too much of a mess here. This blackboard is a bit. So what we are saying is that in this case, simply p times v bar du by dx evaluated between x1 and x0 minus u dv bar by dx evaluated at x1 and x0. So it becomes a very simple thing. P just comes out as a common, because dp by dx term cancel. Two things. I mean, you can check it. But p is never 0. So if you want to make this 0, this must vanish. Then it becomes much easier, because if u is Dirichlet, if u satisfies Dirichlet boundary condition, then this vanishes. This must vanish for arbitrary du by dx at the endpoints. That can only happen if v is Dirichlet also, right? So that means the v is also Dirichlet. When I say also Dirichlet, meaning it satisfies the Dirichlet condition. Okay. Now suppose u satisfies Neumann boundary condition. Okay. That means du by dx is 0 at the endpoints, but u is arbitrary. So then for this to vanish, dv by dx must also satisfy Neumann. So v also satisfies Neumann. Well, we can also consider several examples given here. I think periodic, if you choose periodic conditions, yeah. I mean, yeah, there are several conditions. I mean, I just said the most useful conditions that appear in physics are this one, Dirichlet, Neumann, or periodic boundary conditions. Periodic meaning at the two endpoints, u has the same value, and du by dx has the same value. So the periodic boundary condition, what it periodic means, that u at x1 equal to u at x0, and du by dx at x1 equal to du by dx at x0. That's a periodic boundary condition. So neither of them is 0, but the difference is 0 at x1 and x0. So if we substitute that, what will we get here? So this will give you, unfortunately, so let me just analyze this periodic boundary condition. So that Q becomes P. I mean, so we just want to make the Q vanish. So this must vanish, right? So we are saying, okay, no, I should say P of x1 times V bar at x1 minus P at x0, V bar at x0. Times, because I use the fact that du by dx at x1 is the same as du by dx at x0. So this is multiplying du by dx at x0 because the same, du by dx at x1 is the same. And then from the other point, other piece I will get minus p at x1 times u at x1 minus p at x0. What am I saying? dv by dx, dv bar by dx at x1 and dv bar by dx at x0. This is multiplying u at x0. Okay, but these are arbitrary, right? So condition for the v is that this must vanish and that must vanish. That's the condition. Right? Now, in general, of course, I mean this doesn't tell you that v and dv by dx are periodic, but such kind of a boundary condition is useful, right? Only if the functions which appear in this a, b, c, they themselves are periodic. You see. Otherwise, this boundary condition doesn't. I mean, it's not a very useful boundary condition. So in such cases, the p itself becomes periodic. If p itself is periodic, then you have then basically the condition saying that. So if furthermore p is periodic, then we see that these boundary conditions are self-adjoint. Because if p is periodic, you can take it out. P of x1 equal to p of x0, you can take it out, and then you just get v bar at x1 equal to v bar at x0, and dv bar by dx at x1 equal to dv bar by dx. So, no, not. I mean, the general condition is this. No, but this p is not factored out like that. I mean, it's really p times this whole thing, right? P times this whole thing. When you look at the boundary condition, it is p, this whole thing actually. It's not, when I wrote p, that's a bit misleading. I mean, what I meant was that whatever appears here, you should be evaluated between x1 and x1.
The second term should vanish because u is
Second term vanishes. No. I'm now considering the third situation. This is the periodic. First condition is there is the p is not important for the first condition.
Yeah. From there we found that v of x0
Is Dirichlet, yeah.
v bar of x0 is equal to 0.
V bar is 0, but that's the same as v. V bar is a complex conjugate of v, right? So if v is 0, v bar is 0. Right?
Is it because v bar is not always equal to v?
Why? But if it is 0, it is 0, right?
Yeah, it is evaluated at a point.
Yeah, at that point. At that point, if you say v bar is 0, that means v is 0. Whenever a complex object is 0, it is 0.
It is the complex conjugate of v of x, but it is the point. It is the
function may not be equal.
Function is not equal. Function is not equal everywhere, just at the endpoints. Because boundary condition is only got to do with the value at x1 and x0. The value at x1 is a complex number, not a function, a complex number at that point. And when you say that complex number is 0, then its complex conjugate is also 0, right? Correct? Huh? Yeah, if it was not at 0, of course, then the complex conjugate is different from the original function, right? In the original number. It's not a function. V and V bar are different, right? But when I'm saying that at the endpoint, V bar at x1 is 0, V bar of x1, so then it implies that V at x1 is also 0, right? Clear, right? Yeah, okay. And the same argument holds for also the Neumann boundary condition. Same thing. Because dv bar by dx, I mean, if you use the second one, this is drops out, and you have to satisfy that. So dv bar by dx at x1 equal to 0, but that also implies that dv by dx at x1 equal to 0. Okay, so Sorry. Yeah, if periodic, then this is so. Then this boundary condition is self-adjoint in the sense that V also satisfies the same periodic boundary conditions. Okay, that's I'm assuming that's only if P is periodic. If P is not periodic, then this is the condition that you have is this must vanish and that must vanish, right? So okay, it will be some different condition than the original condition. But if P was periodic, then you get. Okay, so now I think let's go back to some more formal discussion. Some properties of the Green's functions. Correct. Okay. So now, okay, any questions on this? I mean, so far, before I move to the Green's function, I mean, so far we have just discussed the space of functions on which L acts, the space of function on which L dagger acts. And then we looked at some particular cases where L dagger is equal to L. But from now on, I'll just consider the most general case. L dagger may not be equal to L, the general case. Yeah, for this last analysis and so on, I've assumed that A is always positive, that last part, where the weight function had a 1 over A times P, right? The weight was defined as P over A. P is, of course, an exponential, so that never vanishes, right? But, and that's positive, P is always positive. So for this to make sense, A has to be positive, right? So, and in particular, of course, that means it is not 0 also anywhere. If there is a point where A becomes 0, then W becomes infinite and so on. So it's a bit of, so this is I mean, A equal to 0 is a bit particular case because then the coefficient d2 by dx2 vanishes. So at that point, effectively, it becomes a first order differential operator. Right? But anyway, as I said, I will discuss it later on when I discuss the extending this thing to the complex plane. I mean, here so far we are talking about real, one variable, but we will discuss the complex plane situation. And then again, this complex, the second chapter will come back in many ways. Second chapter is really everywhere in this course, you know. Yeah. So let's go back to the Green's function. So what is the kind of equation we want? Right? You remember we said, I mean, we want to find the inverse of these operators, right? So we have, I mean, say something like this LU. U is a vector. U is an element. U is an element of this. I mean, in this vector space, where whatever boundary condition you have chosen for the U, so you are considering a function in that we satisfy that boundary condition, and that is what we label by this vector V, and L is acting on there, and so we would like to have something which plays the role of L inverse. But L inverse should be, this is now a bit, I'm just giving you some intuitive reasoning, intuitive argument. L inverse should be the identity operator, right? Well, if it is an identity operator, what it should do, acting on any function, it should give you back the same function, right? If it acts on any state, it should just, this identity operator should just give you back the same state. So what could it be? Well, so I would think of identity operator as in terms of representing it as a function, This is the abstract notation, right? But now we represent it as a function. I will just write it as delta of x minus y divided by w, right? You see, if you forget w for the moment, if you think of x and y as indices, I mean, you see, when we talked about the finite dimensional case, when matrices and so on, the identity was simply delta ij, right? Identity matrix was its elements were simply delta ij, Kronecker delta ij, right? But now we are working in the infinite dimensional space, function space. So you think of I and j as x and y, labeled by x and y, although they are continuous now, they are not discrete. So this is a generalization of delta ij to the continuous variables, delta x minus y. The reason why we put wx is because the integrals are always defined by the weight function. So in other words, what it does, you see, if I apply this on some function f at y, f at y, then the result of that will be I have to integrate it, delta x minus y fy over wx. But in the integral, always I have the weight function after all, right? Integrals always, when we have a weight function, I'm always defining the integral with the weight function. Okay. So why is that so? I mean, why did I integrate y? Because again, going back to the finite dimensional case, you have some matrix M, which has an index I and j, row and column, right? When I multiply to some vector, I have to sum over this index j, right? So now what is happening? This I is replaced by x, this j is replaced by y, this j is replaced by y, and summing over y is now integral because y is a continuous variable, right? So that's what it is, and it's just that these integrals are defined with some weight function in general. If you, okay, for simple cases, just weight function is 1, but otherwise that. And you want this to be, if it's identity, then it should give you back the same element, f, right? If this was identity operator, so that means Kronecker delta, I would get back v at I, v of I, which means v at x, right? Because I is replaced by x. So the result of this thing should just give me back f of x, if this is the identity operator, right? And indeed that's the case because this is a Dirac delta function. So wx I can set as wy, right? Because this is 0 everywhere except for x not x equal to y. So this w, the only contribution will be when wy will, okay, so the result is this will be, let's say wx goes out, 1 over wx, and then this, when I integrate the y, what will happen? This will all just become wx times f of x, right? That's the, so wx cancel and you get back f of x. So this is the correct definition of the, I mean, that's the generalization of what we know as Kronecker delta to this situation. Okay. So what we'll have, so L inverse, you see, so what I have to do, so the equation is this. This is equal to this, and then I have some L inverse I will label like that, gxy. So once again, think of this x as is generalization of ij. This is the inverse matrix, which is again labeled by index I and j. I is replaced by x and j is replaced by y. Okay. And that's going to be the identity operator. So you have delta x minus y over wx. Here it doesn't matter whether you call it wx or wy, because anyway it's multiplying Dirac delta function, right? So this is the equation we are looking for, and that is kind of, let's say, what we call right inverse, right? Right inverse of this L. Okay, so that's equation. Now, I mean, this was a kind of intuitive argument. The reason why it's intuitive argument I'm giving is because a lot of stuff in the third chapter I didn't cover. I didn't discuss in the third chapter. In fact, the copy you have is not the full chapter. It's only half of the chapter. Okay. The rest of the half of the chapter I didn't discuss because there is all this discussion about the precise translation from the finite dimensional case to infinite dimensional cases. But it was too much, so I skipped that. So in fact, all this is much more rigorously explained in that part which I didn't cover. But for the moment, for our purposes, I think is enough to take this thing. Because ultimately, we are just interested in using this Green's function to solve the differential equations, right? And we'll see that if you can find a Green's function which satisfies this equation, then you can use that to solve the original equation. Okay? So, but now look at this. I mean, this is acting on x. But remember, L is supposed to act on functions which satisfy whatever boundary conditions the u satisfy, right? So what we'll say that g of xy as a function of x, I mean keep not as a function of y, but as a function of x, x must satisfy the boundary conditions. Let me call those two boundary conditions as B1 and B2. Remember, there are two boundary conditions, right? Two linearly independent boundary conditions. So satisfy the boundary conditions B1 and B2. So U. So what my notation is that U satisfies the boundary conditions B1 U equal to 0 and B2 U equal to 0. Okay. I mean, when I say right, like, of course, this B1 has four terms: U at x1, U at x0, du by dx at x1, du by dx at x0. But anyway, it depends linearly on U, of course, right? It's a linear boundary conditions. And the adjoint boundary condition, I will write it as B tilde. So B tilde, which in general will be different from the B1 and B2. B tilde 2, B equal to 0, B equal to 0. Okay. Those are the boundary conditions. So these are the satisfies the boundary conditions. Okay. So since L is supposed to act on functions which satisfy this boundary condition, but Lx, so as a function of x, this Green's function gxy must satisfy the same boundary conditions as the U satisfies. Okay? Because this Lx is acting on the x part here, right? In the same way, you can also define an adjoint Green's function, right? Because after all, you have an L Dagger operator. This is another operator, right? So you have also another equation L Dagger x, and I will use the symbol small g, g of xy equal to delta x minus y divided by wx, where now g of xy will satisfy adjoint boundary condition, satisfy as a function of x, as a function of x satisfies adjoint boundary conditions B1 tilde and B2 tilde. Okay. So these are the two Green's functions you can write on. I mean, I have this operator L and this adjoint operator. For each of them, I try to find out what is the right inverse. Okay. Yeah, some properties now we'll try to get some of the properties. Yeah, first of all, I will need that identity, which is just this identity. I have to write it down somewhere. So remember, this is called the green identity. I forgot to tell you the name green identity, but it's just simply this equation: dx w v bar lx u integral minus the integral dx w u L dagger x v bar equal to 0. Okay. This is actually, it's the boundary terms, but remember we are always imposing the boundary conditions B1 and B2 on the U and B1 tilde and B2 tilde on the V so that the boundary terms vanish. Otherwise, more generally, there would be surface terms, right? But we are assuming that, so here we assume that U satisfies B1 and B2, and the V satisfies B1 tilde of V equal to B2 tilde of V equal to 0, right? So that the boundary terms vanish. This is called the green identity. Okay, so suppose that you can find the solutions, and we will discuss in the later, I don't know whether today or next week, that we'll obtain the necessary and sufficient conditions for these to exist. And we'll show that either both of them exist and they are unique, or they don't exist, or neither of them exists. So we will come to that. But for the moment, let me just assume that it exists. Suppose we can find these Green's functions. We solve these equations. Okay. Then you can obtain the equation, the solution for the inhomogeneous equation. So suppose I have now the equation. We want to find a u which satisfies this equation. Okay. You can find by using these two guys. For example, by let's see, if I choose v. Yeah. So take this Green's identity and choose v equal to the little gxy, v of x equal to little gxy. Okay. Yeah.
Does it have a geometric interpretation for the Green identity?
Geometric identity meaning?
Yeah, interpretation.
I mean, this was this original statement. I don't know. I mean, this was the original thing, which we just said that V L U is equal to U L dagger V. This is just, I'm just writing it explicitly in terms of integrals. That's all, right? That's, yeah, I mean, sorry, this is L dagger. So now if you substitute, let's take V to be this. Y is a parameter, arbitrary parameter, and this is all a function of x here, right? Or everything is a function of x. Then what we find is that this equation becomes this becomes dx w v bar, which is g bar of xy. Okay, I'm integrating x, and then Lx of ux. But suppose Lx of ux satisfies this equation. Okay, then you find here this becomes f of x. Okay, that is minus here. Now, L dagger x acting on Vx, but Vx is g of xy, so you can use this equation. So the WW cancels, and when you integrate, you just have ux, dx ux, delta x minus y. That just gives you u of y, right? So this minus u of y is equal to 0. That's the equation. Okay, so you can find what is u of y. See? So u of y is simply this, or just to, I mean, so u of y is integral dx wx g bar xy f of x. Many times I'm not writing this, it's understood this, everything is in the interval, x0 to x1. When I write this integral, it always means whatever interval you have chosen, everything is between x0 and x1, right? But I'm not going to write, otherwise it's too much time it will take to write all this. So all these integrals are in that interval. So this way, you see, you are using this Green's function, you are able to construct, to find a solution of that equation. Similarly, suppose I have the equation, the adjoint equation, L dagger x acting on, say, some v equal to some function, I don't know, h of x, let's say. Then you can again now choose, now you can choose u equal to capital Gxy. Okay. So this was one. So this is a solution of that equation. What I'm saying is that this is the solution of that equation. Okay. Now similarly, if you look at the adjoint equation, again inhomogeneous equation, now again use Green identity, but choose u equal to g of xy, capital G of xy. So u of x equal to capital G of xy. Then again, let's look at here. This gives you Lx acting on capital Gxy, but that is the delta function divided by weight. So weight cancels, and integrating delta function just gives you v bar at y. So this gives you V bar at y equal to, I take this on the other side. After all, this minus that's equal to 0. So now you have dx wx, and u is capital Gxy. And then L dagger V is equal to h. So I substitute that back here, so you get here h bar of x. So this is an equation for the V. If you want, you can just take the complex conjugate on both sides. So take the complex conjugate, this becomes V here. W is real, but there's a G bar, and the H complex, it just becomes H. So that gives you the solution for the adjoint differential equation. Yeah. Now let's continue. There are several properties. Let me just describe some or list some of these properties. Yeah. So now you can ask the question, what is the relation between these two? Is there some relation between these two, capital G and small g? And again, that everything you obtain by simply using this Green's identity. There's a lot of stuff you can learn from the Green's identity. Okay. So let me do the following. I take say in this expression, I take u of x equal to capital G of x, y, let's say, and v of x, I choose to be small g x, y prime, let's say. Y and y prime are free parameters, arbitrary. Of course, always in the interval x0 to x1. So if I plug this here, the first term, Lx acting on capital G is delta function, w cancels, and that integral simply gives me, okay, let me do it in 2 steps. So when I substitute that, I will get dx, the v bar x, which is g bar of x, y prime, right? And then Lx of u, which is that, the weight functions cancel, so that's why I didn't write the weight function, and you get here delta x minus y, minus dx. Now u is g of xy, okay, and L dagger x acting on v. V is this Green's function, so it's delta function. Bar doesn't matter because these are real. W cancels, and you just get delta of x minus y prime, because this is g of x y prime. So you integrate now. So that is equal to 0, but what is that? This is, I can do the x integral. So this gives you g bar of y prime minus, here x becomes y prime, so minus g of x y prime, y prime, y prime y, y prime y, that's equal to 0. Yeah? This is, you see, this equation is very much like what we would say adjoint. If you think, remember we said that these two, in the discrete version, in the finite dimensional case, these two would be the row and column, right? Say this is I and j. Huh? Now that is a transpose, because that is exchanging this becomes ji, and here is a complex conjugate. That's exactly taking the adjoint, right? So we are saying that the capital G is the adjoint of small g, and vice versa. If you again take that analogy of these playing the role of indices, right? But okay, ignoring, so one important relation from here is that g of y prime is equal to g bar of y prime y. It's the same. I just took the complex conjugate of that. So there's a relation between the two. So 2 things it tells you. So it tells you that if capital G exists, small g exists, right? And vice versa. They exist. It has not shown that it is unique. We have not shown that yet, but we will see. We'll show that it's unique by explicitly constructing the Green's function. Okay? We'll explicitly find the solution of this equation. Explicitly, to some extent, yeah, explicitly. and we'll show that there is a unique. I mean, either it doesn't exist at all. There is some particular condition has to be satisfied. If that condition is not satisfied, the Green's function doesn't exist. Okay, but if that condition is satisfied, it exists and it is unique. There is only one solution. So, okay, we will show that by explicit construction. So at the moment, all we can say is that if this exists, that exists, and vice versa. Second thing you see is that we said the little g satisfies the boundary condition b1 tilde and b2 tilde as a function of the first argument, x. Now here, whereas capital G satisfies b1 and b2 boundary conditions for x, for the first argument. But here the arguments are exchanged. Okay? So what this equation tells you is that g bar y prime y satisfies b1 tilde and b2 tilde boundary conditions on y, on the second argument, right? Because this y is the same as the first argument of small g, and the first argument of small g satisfies b1 tilde, b2 tilde conditions. So it's very precise. I mean, now what we are saying is that if you look at this x and y, as a function of x, it satisfies b1, b2 boundary conditions. As a function of y, it satisfies the complex conjugate of b1 tilde and b2 tilde equations, right? Because it's the g bar which satisfies b1 tilde, b2 tilde. If you take the complex conjugate, g will satisfy the complex conjugate of b1 tilde, b2 tilde equations. So that is the important point. So this, as an argument of this, it satisfies b1, b2 conditions. As an argument of that, it satisfies b1 tilde bar and b2 tilde bar conditions. And the same way here. So the little g as a function of y satisfies b1 tilde, b2 tilde, but as a function of y prime, which is the first argument here, will satisfy b1 bar and b2 bar conditions. So yeah, that's something. There's a few more, let's see, a few more properties. So this was in general, but what happens in the particular case when this is self-adjoint operator? So L dagger is the same as L, right? So therefore, okay. So the little, and furthermore, suppose it's, yeah, in fact, let me see, self-adjoint operator. So not, for the self-adjoint, I cannot say much because still the boundary conditions may be still different, you see. But let's suppose it's Hermitian operator, which means not only that L dagger is equal to L, but these boundary conditions are the same. B1, B2 are the same as B1 tilde, B2 tilde. In that case, there is no difference between these two equations, right? So g of xy must be, small g of xy must be the same as capital G of xy, right? So for the Hermitian case, I just write that thing down. If L is Hermitian, Lx equal to L dagger x, and B1, B2 are same as B1 tilde, B2 tilde, that is when you call the operator Hermitian. Okay? In that case, there is no difference between these two equations, right? So in that case, g of xy equal to capital G of xy. Okay. Combining that with this, you see that this is the same as g bar of yx, right? But this is generally true, not just for Hermitian, right? So I just substitute small g of xy is the same as capital G bar of yx. This equation is only true, the first part is only true for the Hermitian. Then it's a Hermitian operator. But this is equal to that in general. So what we are saying is that for Hermitian operator, capital Gxy is the same as capital G bar of yx, which is again, if you think in terms of the row and column, so if you replace x by I and g, y by j, you get g of ij is g bar of ji, right? Which is g is Hermitian. That's what. So this is the situation where, so the L is Hermitian, then the Green's function is also Hermitian in this sense. If you take this as I and j indices. It's like is analog of the Hermitian in the xy situation. Okay, that's what else I have to say here. And in the particular case, I mean, the situations where Lx is a real operator, you know, where Lx was in general a times d2 by dx2 plus b d by dx plus c. If a, b, c are real, then the Green's function will be real also, because you have just the real differential operator will act on the real vector space, right? So that will be real. So if in that case g bar is the same as the g, so in that case it says the Green's function must be symmetric in xy exchange. That's only true for the real operator. Otherwise, it's more generally it will be this relation. There are a few more points I have to say here. Let's see. Okay. Okay. So now let us. How much I should. Okay. So now some other properties we need to obtain, and for that let's now examine this equation in slightly more detail. I think erase all this part now. Let's look at this equation in more detail. You see, this equation. Strictly speaking, I have been a bit, I mean, I'm not being very rigorous in all this discussion. This is a generalized function, right? We saw the Dirac delta function should be correctly understood as a generalized function, okay? So right-hand side is generalized function, left-hand side also should be thought of as generalized function, okay? So one should think of this Green's function as a generalized function, and then, of course, if you think of a generalized function, the derivatives always exist, as we saw before. So these derivatives will act on the generalized functions, and you have a equality of two generalized functions, right? However, if you look at, let's look at the specific explicit form for the second order operator. You have ax d2 by dx2 g of xy. Sorry, I mean write. Okay, let's write full thing. G of xy plus bx dg by dx xy plus cx g of xy. This is supposed to be equal to delta function x minus y over wx. Here you can either put wx or wy, it doesn't matter, because it's multiplying delta functions. First of all, you see that we know that whether or not you consider it a generalized function, this Dirac delta function has a local value. I mean, for all x, whenever this argument is not equal to 0, right, it is 0. Delta function is 0, right? So what we are saying is that when x is not equal to y, then right-hand side is 0. Okay, which means this Green's function, when x is not equal to y, I should be always it satisfies a homogeneous equation when x is not equal to y. So it should be a linear combination of a fundamental set of solutions, or the homogeneous equation. You know that we saw there were two linearly independent set of solutions, fundamental set of solutions. So this G I can always express as a linear combination of the two when x is not equal to y. Okay. So here is my say x, and let's say the value of y is some particular point. I fix y because as far as this equation is concerned, y is fixed, right? I'm only varying with respect to x. Right? Now, in this region, when x is here or when x is here, in each of these regions, this Green's function must be a linear combination of two. Let's say, suppose u1 and u2 are the fundamental set of solution. Is a fundamental set. Set of linearly independent, right? Of course. Solutions of the homogeneous equation. Okay. In that case, this Green's function must be a particular linear combination here of u1 and u2, and in general another linear combination of, right? If it was the same linear combination, there is no way I will get at x equal to y you should get delta function, right? If it was the same linear combination of the two sides, you would not, the right hand side will be simply 0, So what it tells you that it cannot be the same linear combination, right? Linear combination appearing here and linear combination appearing here must be different. Okay. I mean, say here for x greater than y, suppose it's about is equal to C1 U1 plus C2 U2. So I should be more explicit. When I say this is a linear combination, it means it's independent of x. These are constants as a function of x, right? But it could depend on y. In general, it will depend on y, right? Plus C2 y U2 y. I mean, if I fix a y, then okay, this is a constant for a fixed y. But if I change y, this in general this could depend on y. That doesn't contradict this because this differential operator is only with respect to x. It doesn't care about the y, right? Similarly here, it may be another in general linear combination, d1y u1x plus d2y u2x. Okay. If C1 was equal to D1 and C2 was equal to D2, then it is the same linear combination throughout, right? For a fixed y, keep a y fixed. Okay. If C1 was equal to D1 and C2 was equal to D2, it would be the same linear combination. And then it would have just, I mean, when you apply the differential operator on that, it will be a 0 everywhere, including at x equal to y. So clearly, these are not the same linear combinations. So they are not equal. But now let's further look at the property here. If you look at this equation, you remember we saw that the derivative of the step function was a Dirac delta function. Step function viewed as a generalized function. Derivative of that was a Dirac delta function. So, I mean, it's natural to then think of that on the right hand side there should be some step function, right? However, you see, if the Green's function itself was a step function, that would be a problem because, okay, this will give you a delta function, but then I have another derivative of the delta function. This is two derivatives, right? So that will give you d by dx of delta function of x minus y. On the right hand side, there is no derivative of delta function, right? So g of xy cannot be a step function, right? So in other words, g of xy itself must be continuous as you cross from this region to that region, right? Because if the g of xy had discontinuity, as you come from here and as you come from here, there's a discontinuity, then the derivative of that would have given you a Dirac delta function, right? So this tells me that the Green's function itself must be continuous, okay? When you approach from here or approach from there, the value of g should be the same, right? However, not the first derivative. So first derivative of the Green's function must have a step function, because then the second derivative will give you Dirac delta function. Okay? So that's the idea. So the discontinuity must be there, not in the function, the Green's function itself, but its first derivative. Okay? So this is the main condition. So the continuity conditions are the following. So let's see what are the conditions. So if I try to write so dg by dx as something, I don't know, some alpha times h of x minus y, the step function. You remember the step function, this was defined as h of x minus y is equal to 1 for x greater than y and 0 for x less than y. And it's the derivative of that will give you Dirac delta function. So it should be something like this. So what are we saying here? So if you look at this, so if I plug that in here, you'll get here. I mean, so this is in general a function of x and y also. Everything is a function of x and y. So this could be a function of x. It's not a problem. X and y. Then it is saying that so if you take the derivative, so you'll get here a of x alpha xy, and the derivative acting on that will give you Dirac delta function. Okay. Plus you see, I mean, as I said, the d by dx can also act there, but that is not, it's not a Dirac delta function, it's just a step function. So I'm looking at the coefficient of Dirac delta function to match it with the right hand side. So what this is saying is that this is equal to, and none of the other things give you a delta function. This doesn't give you a delta function, this is only step function. This is of course not, I mean, this is even the integral of, if the dg by dx is a proportional to step function, then the g itself is an integral of that somehow, right? So that's not going to be a Dirac delta function. Okay, so only Dirac delta function comes from here. When the d by dx, extra d by dx acts on that, right? So that is that. So this must be, so this coefficient must be equal to that 1 over w, right? So this must be, so this coefficient must be equal to 1 over w. Okay. Because this was the coefficient of Dirac delta function here. That, okay.
W is a function of x, correct?
Sorry?
W is a function of x.
W is a function, but I mean, this is all at x equal to y. After all, this whole thing is multiplying Dirac delta function, right? So you can just set it to y equal to y. I mean, this is this Dirac delta function is 0 whenever x is not equal to y. So the only non-trivial condition is when x equal to y. So basically, we can just substitute everything by y here. So alpha is some function of y. So that's what this is telling you. I mean, so what is this saying? So we are saying that. So therefore, so what we are saying is that dg by dx, as x comes from, as x goes to y plus epsilon, right? That should be equal to alpha y, right? Because h of x minus y, when you're coming from the right hand side, is 1. Okay, but alpha y we said is simply 1 over a w, a at y, w at y. On the other hand, I mean, dg by dx is not just that. I mean, there are also other pieces. This is the piece which gives you the discontinuity, which gives you delta function, right? So more appropriately, what I should do is to look at the difference dg by dx as you come from y, x going from y plus epsilon from the right hand side or the left hand and the left hand side, and take the difference, because all the remaining part will be continuous in that, so they will cancel. So okay, it's better to say it like this. So take this, I mean this plus continuous pieces, right? That is what dg by dx will look like. Huh? Dg by dx should look like that to give you such a Dirac delta function. The discontinuity is here, and the rest of the pieces are continuous. Okay. And what we said already, that this alpha is 1 over. So alpha, remember, alpha is 1 over aw. So what it's saying that if you take the, if you take this dg by dx as x goes to y plus epsilon, y plus 0, I mean as you approach, minus dg by dx at as x goes to y minus 0, so coming from the left or from the difference between the right and left, that should be equal to alpha, but their alpha is 1 over aw at y. So this is the basic equation we have. That the derivative has discontinuity, but also we said that g itself must be continuous. G must be continuous, otherwise already the first derivative will give you a delta function. So second derivative will give you delta prime, I mean one more derivative. So this is one equation. Another equation is a continuity. G of xy as x goes to y plus 0 should be equal to g of xy as x goes to y minus 0. These are the two equations. Okay. Yeah, maybe, okay, I should just, so what is the strategy now? We said x, for x not equal to phi, this must be linear combination of the fundamental solutions. Sorry, this is x. And similarly, for x less than y, there should be another linear combination, right? But then they must satisfy these conditions, this continuity and discontinuity conditions for the g and the derivative of g. Okay, so you have to plug that in here. So you will get conditions on these coefficients c1, c2, d1, d2. You'll get two conditions. Okay, and so then we'll analyze further from there. Now it's not enough time. Can I? No, I think it will take longer time than that. Yeah, it will take longer, more than 15 minutes. So I think I will stop here. But please, we'll start from here, Monday. I think it's Monday. We'll start from this continuity equations and the fact that you can express as linear combination of a fundamental set of solutions, and then we'll show under what conditions the Green's function exists, and if it exists, we'll show that it is unique. Okay, so it's a necessary and sufficient condition for the Green's function to exist.